Welcome back, recruits, to the continuation of Phase 4 of AP Calculus Bootcamp. Today's operation pushes further into contextual applications, specifically focusing on topics 4.4 through 4.7. Remember, this unit accounts for 10 to 15% of your AP Calculus AB exam weighting. Status is Mission Go. Here is your mission briefing for deploying the derivative. Your objective is to translate verbal scenarios into mathematical protocols. We have 3 primary waypoints today: tracking multivariable changes linked by time in related rates, weaponizing tangent lines for local linearity, and breaking indeterminate limits using L'Hopital's rule. Let's establish field intel for topic 4.4, the time sink mechanism. In related rates problems, variables like x and y do not drive each other. They are both driven by a hidden third variable, time. Therefore, our core protocol is the chain rule. Differentiating any variable requires you to multiply by its rate with respect to time, giving you expressions like dx dt and dy dt. Here is your standard operating procedure for related rates. We operate on a strict deployment timeline. First is the static phase. Draw your picture and link the variables with a geometric equation. Next is the dynamic phase. Take the derivative with respect to time, appending your ddt terms. Finally, execution. Substitute specific, instantaneous field data and state your final answer with exact units. Hazard detection active. Beware the ambush point. Substituting changing variables before taking the derivative is a fatal error, because the derivative of a constant is 0, which eliminates their rate of change. Your rules of engagement are clear. If a value never changes, plug it in before differentiating. If a value changes over time, plug it in after differentiating. Moving to topic 4.6, visual recon for local linearity. Here is our tactical advantage. If you zoom in far enough, every smooth curve looks like a straight line. We weaponize the tangent line equation to approximate our function, f of x, when exact coordinates are locked out or unknown. Your estimation status relies heavily on concavity recon. Approximation accuracy relies entirely on concavity, not on whether the function is increasing or decreasing. If a curve is concave up, it is shaped like a bowl, meaning the tangent line sits physically below the curve, resulting in an underestimate. If it is concave down, like an umbrella, the tangent sits above, resulting in an overestimate. Special directives for topic 4.7, indeterminate forms. When navigating limits, you may hit ratios of 0 over 0 or infinity over infinity. These forms are not numbers. They are encrypted glitches indicating a limit might exist, but standard algebra cannot decode it. When access is denied, you deploy the protocol, L'Hopital's rule. Strict communication protocols must be followed to decode L'Hopital. Setting an equation equal to 0 over 0 is a fatal protocol violation that will drop your AP point, because 0 over 0 is a label, not a mathematical value. Your mandatory cipher requires you to verify the limit scanners independently. You must explicitly show that the limit of the numerator equals 0 and the limit of the denominator equals 0 before clearance is granted. Once cleared, you initiate the execution protocol. You will apply an independent strike, differentiate the numerator independently, and differentiate the denominator independently. Critical intel: this is not the quotient rule. You must strike the top and bottom targets separately to find your limit. Time for the Phase 4 debrief. Related rates successfully deployed the chain rule for tracking multiple variables linked by time. We avoided hazards by strictly substituting data after differentiation. Tangent lines were weaponized for local approximation, with concavity verifying our accuracy. And L'Hopital's rule broke indeterminate forms, using independently verified derivatives. Unit 4 is secured. End transmission. For more AP Calculus worked out free response question solutions, like and subscribe to get your FRQ on.